Great. So last but not least, our last presenter, Dr. Hercules Konstantopoulos, Chief Data Scientist from Upflow. Growing up by the mountain of northern Greece, Hercules developed a fascination with the night sky and all its intrigue. After a career as a researcher in astrophysics that spanned 10 years and in 4 continents, he became drawn to addressing a greater variety of data-related problems. Data science ensued with work on sustainability, renewable energy, and enterprise software. His work focuses on converting information into strategy and on crafting useful tools, apps, and visuals. Hercules, the floor is yours.
Thank you so much, Ghazal. And thank you so much for having me. It's very exciting to be at Pivot. It's my first time here, so it's very cool to be here as a presenter. So we know that the energy sector as a whole has heaps to gain from using AI to enhance its techniques. We know that conceptually, we hear about this a lot. Everybody tells us this, and I'm usually the one telling you that. So we've heard a lot about it. There's an awareness in the sector, I think, in this particular context where we are today for Pivot, on the exploration, drilling, and heavy side of development as an obvious area to make techniques, create new techniques, and make operations better. But I want to focus in this presentation about existing facilities. We've been hearing a lot of big buzzwords coming from AI in the press. Generative AI, ChatGPT are the kind of flavor of the day. The huge advancements that are making big waves. The next word you're going to be hearing most likely is orchestration. Orchestration is a really big word when it comes to AI helping to run existing industrial facilities. Orchestration is the idea that machine intelligence is very targeted, and it doesn't really have a good grasp of many different areas of activity. So that's the next wave that you're going to be hearing a lot about. So improving the output of our steam fields and dropping the cost of generation in geothermal is especially relevant, I would say, in the current wave where wind and solar are seen by the lay public and by a lot of policymakers as clear winners in the renewables race. Lowering the cost of operations, LCOE and all that kind of stuff in geothermal is obviously a big deal in that context. So let's imagine that in our travels we encounter a wizard. The wizard says, hey, what if we could magically boost the output of every existing facility by a couple of %? No new equipment, no expenditure, just redirect some mass and get some free megawatts. Obviously, more geothermal means less coal, oil, and methane burned to make power, so that's a very appealing prospect. And there's the particular case of, well, reality where we want to be reducing fossils, and the use case that will become a use case of California ordering 11 gigawatts of new electricity resources after the 2020 blackouts, and ring fencing a kind of a segment of 1,000 new megawatts of so-called zero emission baseload, a puzzle piece that is shaped like geothermal, basically, even though it's not explicitly mentioned that way. So gigawatt is roughly 300 new wells, right? That's expensive. So how much is accessible through this wizardry of kind of 2%? Installed capacity in the United States is about 3.7 gigawatts. 2% boost is 75 meg. That's about 7% of that new mandate. So in terms of financials, 75 megawatts is roughly 20 wells, at $10 million a well, 20% failure rate. That's a cool $250 million. And that's US dollars, the expensive kind of dollars, not the ones I've got in New Zealand. So that's kind of a big deal, right? The spoiler is obvious. The magic is AI. This is the point of this session. So I'm not talking about actual magic. So let me tell you about a project that we're running at Upflow. GOOML stands for Geothermal Operational Optimization with Machine Learning. It is a workbench for geothermal field optimization. I'm sure people have come up against digital twins, but in case some people haven't heard the terminology, a digital twin is a fully functional representational of representation of a set of machinery in a digital domain that then can be interrogated to produce forecasts of what would happen if I were to change this. They're used for troubleshooting, for root cause analysis, for predictive maintenance, and they can be used at length for optimization. In our case, we create a digital twin for every steam field, and then we tweak it infinitely to suggest strategy to expert operators. A lot of R&D went into this. It was funded very generously by the Department of Energy in the US through a grant by the Geothermal Technology Office, to whom we're incredibly grateful. It was undertaken in collaboration with the National Renewable Energy Lab in the US, which means that there's real physics, real thermodynamics all the way. It was also co-founded in kind and with data and with expertise, crucial expertise, by our three commercial partners, Contact Energy and NTDA in New Zealand, and Ormat Technologies in the US, which meant that we had real world data and real world expertise going into this project. And the strategies that Ghazal suggested kind of got the seal of approval, definitely got the seal of approval from our operators to say, yes, this would boost my output by at least 1%. That was the objective always. And now we're building this into software so everybody can get access. What's the whole point of it? We're using the wrong tools. We basically have operators at our desks using Excel. They don't have access to better tools. The linear algebra that they have to do in their minds to solve the thermodynamics means that they default to a few strategies that they know work. When the trading desk calls and they ask for a few more megawatts, they have a few quick access strategies in their heads to get those extra megawatts. They don't have time, given these tools, to create new strategies. And in their BAU, in their jobs, they're engineers, they have to do real engineering. They don't have time to solve equations all day long. This is really the point. This is really the problem we're trying to solve. We've approached this through a components modeling approach. We have just a component, mix and match everything that makes up a geothermal steam field. This is why we call it a workbench. We don't have to create a new model for each well or each steam field's complement of wells. We just take everything from the system and create this digital twin. And I mentioned before with thermodynamics, actually there was a comment when we were promoting this session on LinkedIn. There was a lot of interest, and somebody said, hey, yes, AI is good, but make it real physics, please. And I was so pleased to see that comment, because obviously it's very easy to get excited about AI and get carried away and say, okay, yeah, statistics will solve all these things. It's not quite that simple. So we need to make sure in our facilities the thermodynamics are respected every step of the way, because there's real risk to facilities. We can't be frivolous about this. We can't, there's real pipelines, real people walking around steam fields. We have to be very, very careful what we do. So with Ghazal, there's thermodynamics involved, and every time we use a neural network, we use physics-informed neural nets. We use Fission, which is a code base that ensures that we've got physics baked in there. So facetiously, he asks, how hard can it be? This is a diagram. This is a kind of component diagram from one of our actual steam fields. There's 175 interconnected components that were needed. That's the minimum set of components needed to describe the system. There's more things that we don't need to describe the system that don't have an outsized effect. So obviously, when you have dozens and dozens of valves, every time you change one, it has an effect on the rest of the system. So this is what I was trying to describe when I was asking you to imagine somebody at the operator's desk. It's kind of impossible to see how this will all work together. It's not impossible for a machine to do this, though. So let's see how we offload all of this hard combinatorics and algebra and linear algebra to a machine. One of the techniques I want to describe to you is reinforcement learning, which has a lot of applications in this field. It's generally ungraciously called the brute force approach. It is nothing but it basically is a trawler for the whole parameter space that our human brains cannot traverse. An agent, which we can think of as a bot or a robot or an algorithm, takes an action, meaning that it makes a minute change to the steam field, maybe changes a valve by 1%, and then observes the effect that this has on the whole rest of the system. and then decides based on a reward function that the operator decides that has set whether this is a good thing or a bad thing, and then takes a further action after that. So let me show you an animation of how this all works. It's going to run through a couple of times, so don't worry if you don't catch it the first time. On the left-hand side, I've just got power. This is an experiment we ran with one of our actual facilities. There's historical data, 18 months worth of it, and then the agent tries to beat history by making changes to the steam field and observing how these would have affected the system based on all the information it has on how the components work together. On the right-hand side is a little representation of this training. On the horizontal axis is epochs for technical people or for AI people, or training steps. So what I was talking about before, making one minute change to the system, that's one training step. There's 1.5 million training steps there. So already you can see how long it takes for this to, how long it takes to do the algebra. The vertical axis is the reward, which is balanced at 100, being I did just as well as the historical data, and anything above 100% is upside, is extra megawatts. So what the agent does is it kind of goes through this parameter space, it tries a few things and observes and sees what kind of things work. And you can see in these big vertical jumps that on a couple of occasions, it has some massive breakthroughs that unlock a part of parameter space that it hadn't traversed, and it stays in that part of parameter space to figure out what else it can do until it balances out. I'll tell you that this experiment in particular was very conservative. So we wanted to make sure that this was very, very realistic and very actionable. So if the agent was only allowed to do very small things that an operator can do remotely by hitting a telemetry button and changing a valve, not very complicated things that might take more engineering. Beyond that, there's more complicated techniques that can be used, or not necessarily complicated, but a little bit more involved in terms of interpretation. We use genetic optimization as well, which is a similar technique in that it makes tweaks, but it tests them in a different way. So it's a technique that's generally used in biological sciences and biotech, and it essentially treats a change to the system as a mutation. So it's a gene. We have a new gene in our population. Let's see if it survives. The survival of the gene, of course, is informed again by a reward function that the operator sets. Does it make more megawatts? Does it free up some math in this part of the system that I know is constrained? It can be a little more creative. We keep them in accordance to their observing these rewards. So I'm not going to dwell on this too much. It's kind of similar as before. On the left, we have the agent changing things to see what they do. On the right, we have a representation of this fictional steam field that we have as a test bed, which is actually synthesized data based on real data. So we keep our simulations realistic as well. And you can see just the illustration, the animation here, just to illustrate how many changes are happening throughout the system, how they're propagating, and how this is something that really is best left to machines, because nobody wants to do all this algebra, definitely not on a spreadsheet. The future part that's exciting about this slide is that with genetic optimization, we're planning to start designing steam fields, going one step beyond optimization and saying, well, a gene could be the physical dimensions of a flash plant, right? If the separator were this dimension, then we can start tweaking our steam fields. So the future is very exciting right now for AI. I mean, it's an incredible field to be involved in. There's incredibly new things happening every day. This illustration here is just to point out that in the current phase, in the energy sector and in most sectors, we're represented by the image on the left, where the machines are sitting alongside us. This machine augmentation, artificial intelligence, is there to help us with things that take too long or are too tedious or are just not fun, you know? So in the next stage, it's conceivable that we will have, after a reasonable period of validation, an offloading of tasks to machines. And a lot of the energy sector, the parts that are not putting anybody at risk, can be automated. And that's the future we need to be looking ahead to, a future where we're not doing tedious tasks anymore, or, we're working less, or we're just making energy a lot cheaper for people, which is a really, really important thing. So it's a very exciting future. It's only the beginning for the energy sector. So it's all a really great place to be. So thank you very much.